Hello and welcome. My name is Shahryar Abbasi. I'm a senior DevOps cloud architect with AWS Professional Services. In this session, we'll learn how Baxter has innovated digital health connectivity with AWS. Joining me today will be the Senior Director of Digital Products IT, Mike Butler of Baxter Healthcare. Let's take a quick look at our agenda. We'll first begin by learning about Baxter and its mission of saving and sustaining lives. Mike will walk us through the Baxter's digital transformation journey and share the design challenges that came with it. Then we'll do a deep dive into a solution architecture to address those challenges. Finally, we'll end with key takeaways and learnings.
Thank you, Shahryar. Thank you so much for having us, having me here today, and having us share our story. Before I jump into an overview of Baxter, our digital transformation, and our challenges, I'd like to thank the TrueView team, R&D, IT, across the board for helping make this solution possible. But again, thank you. It's great to be here. So Baxter, who are we? Where do we operate? A little bit about our business before we jump in to the materials. Baxter has a 90-plus year heritage of saving and sustaining lives. Strong global business, operate in all regions of the globe, one of the most trusted brands, a traditional manufacturing company that's been coming into the digital age. Our mission, again, save and sustain lives. It's one of the great things about working at Baxter is we can say our products truly make a difference. When people ask me, what do I do for a living? I tell them our mission. I say, I save and sustain lives. They ask, are you a doctor? I say, no, I work in IT. And they say, how is it possible that you save and sustain lives in IT? And all of our products, all of our devices are beginning to have connectivity to the internet. They're complex therapies where our caregivers, healthcare providers need help, or our patients need help in delivering the therapy, and technology is helping us do that. So our treatments, almost one is given every second of the day, every day of the year. We sell our products in over 100 countries, manufacture in over 40. And then we truly are a global company with $12 billion in sales around the globe. Our business units, all of them are therapies and care that's needed at a critical point in time. They're not things you sign up for, but you're happy they're there when your friends and family need them. Advanced surgery, surgical glues, biopharma solutions, our contract manufacturing, fill and finish of drugs, clinical nutrition, parenteral nutrition when a patient can't take food enterally, the ability to provide that nourishment to a critically ill patient, medication delivery, infusion pumps for pumping those fluids, pharmaceuticals, anesthesias, gases for surgery as well, and then renal care, our hemodialysis and peritoneal dialysis businesses. All again, critical care that you need at the point, at the right point in time. What we're going to talk about today, though, is acute therapies. Acute therapies, we make a device called a CRRT device, continuous renal replacement therapy. Just like ventilators has been in high demand during COVID-19. And it's a complex therapy where we take blood out of the body, filter it, and put it back in when your kidneys are not working. And so we're going to talk a little bit about that therapy, that solution, and that how we're using the data from those devices to improve outcomes. But before we do that, let me give you a little bit of background on our digital transformation. Baxter's had a drive for digital transformation for a number of reasons, like most companies: cost saving, security, agility, time to market, and then we have had aging legacy technology. For Baxter to make this transformation, we first had to make an IT transformation. To embrace this, we set a North Star as a business, so a top-down, empowering our people and our customers to reach their full potential by driving data, insights, and deep partnerships to advance our mission of saving and sustaining lives. To do that, we first had to focus on IT transformation. Like a lot of companies, we had been on-premise, legacy application stacks, and so we first had to focus on achieving scalable service delivery. Really, the first 2 years of our journey here have been around lifting, shifting, moving, improving our applications to the cloud. That journey involved retiring 3 primary data center hubs, over 1,400 applications, and really first and foremost focused on team development. The team I mentioned earlier that has helped enable these solutions had to learn and grow and adopt the capabilities of the cloud. This journey really shifted our mindset from a data center one to a cloud-based one. And you'll hear about this solution today, and we call it TrueView, where we've made this shift, where we have moved to serverless application infrastructure, low fixed cost, and high agility enabled to deliver solutions around the globe. One last thing before I leave this, and we made that initial shift to the cloud for cost savings. And so we did that over the last 2-3 years, and we've achieved that now. And so we've mapped out what's next. And so we want to share this TrueView solution with you as how we think many of our applications are going to make this same transformation. So digital transformation. Now that we've done the IT homework, standardized, modernized, and have a data-focused organization, how do we transform our products? How do we move from a complex therapy to something that's more understandable, more accessible, and better results overall for our customers? A little segue before we dive into the meat of the presentation. We did set 3 areas of focus: digital health, customer experience, and digital core. Those 3 pillars are all based on our digital backbone or our digital enablers. AWS has been a great partner here for us and really given us many of the building blocks we needed to get started and to advance. So our design challenges in acute on our CRRT devices. Here's a picture of one. This is our Prismax device. Again, critical therapy at a critical point in time and some complexity. Blood is taken from your body, filtered and cleaned in this device and sent back in at a critical point in time for you. So 3 really key design principles or challenges here in front of us. How do we deliver a complex life-saving therapy? Innovate in a highly regulated space. These devices have many-year life cycles. It's not a flip of a switch to change that device. So how do we design in a way that makes us flexible to take advantage of cloud, but protect the device? And then how do we give customers better insights to the therapy and better control of their data? So TrueView, what is it? These Prismax devices, first and foremost for the hospitals for where the devices are being used, auto documentation, understanding what happened on the device and getting that into the hospital system and connected to the patient record. So we'll commonly talk to this as SureSource or TrueView Connect. TrueView Connect allows us to get the data back to the EMR system so the hospital has better understanding of the treatment that's happening on these devices. The second piece, and we're going to do a deep dive into this with Shariar, is TrueView Analytics, or this data-driven consultation. We take anonymized data from the device, take it back to the AWS cloud, and present to our sales teams and consultation teams aggregate data on the clinics on how the therapy is being delivered. So finally, it comes together in a solution that segregates the device from change, allows us to take advantage of the data that's coming from the device and get it into the hospital EMRs, and then gives us insight to the anonymized data at Baxter and gives the customer a better insight to how they're running their clinics, running their point of care. All right, so everybody's here to see the solution architecture. I'm going to hand it off to Shahryar to do a deep dive on the solution.
Thank you, Mike. Now let's take a look at the solution architecture deep dive for the TrueView platform. Before we get into the architecture, we set aside specific goals for ourselves so that we can focus on the goals themselves and then bring about the requirements before we create the architecture. The first and foremost goal that we set for ourselves was to focus on the therapy rather than concentrate on the infrastructure. In that, we wanted to spend majority of our time in creating solutions rather than managing servers. We also wanted to take advantage of the AWS serverless ecosystem, such as using AWS Lambda, running our code without managing servers, and using Amazon S3, for example, for using an object store without worrying about scalability. We also wanted to leverage the solution that we built as a platform so that we can make it modular and accessible for other parts of our solution itself. We also wanted to use and utilize AWS's pay-as-you-go model, and as we scale, we only want to pay for the resources we're using. With the goal set, we started to work through the requirements for the solution itself. First, since we're dealing with the physical device, we wanted the device communication to be done securely to the cloud. Once we have data coming in with a securely connected device, we wanted to be able to manage the data and run analytics on it. Afterward, once the data is stored and we have ETL processes working, we want to be able to give access to that data securely to specific users. We also wanted to keep in mind that we are going to be integrating with Baxter's existing enterprise services, such as Okta for identity providing as an identity provider, Splunk for logging and monitoring, using Atlassian Bitbucket as a CI tool of choice, and using Slack for the communications portions for operations. And as we developed all of these pieces, we wanted to use agile methodologies and also create CI/CD pipelines so that we can iterate on the infrastructure and apps separately and deploy them out at any time we choose to do so. With those requirements set, let's take a deeper look at the device communication side. The challenge we were addressing here is that the existing product in the field required physical access, where we had to download data from the device itself to a laptop. Before doing so, we had to schedule an appointment. Once the data was downloaded, we could run analytics on it on the laptop itself, and at some point, have that data uploaded to the Baxter Central servers. The solution we came up with here was to add remote connectivity, where the Baxter team created a digital communications board where we could run the IoT SDKs using C++. We also wanted to ensure that we have encrypted communication in place and that the communication is both authenticating the endpoint on the AWS side and AWS is authenticating and authorizing the incoming device to connect to it. In this case, we used TLS-based mutual authentication. Once our solution was in place, we could start gathering real-time metrics, near real-time metrics from the device itself, and enabling us to do proactive monitoring of the devices. Overall, with the solution in place, the physical access to the device in the hospital was no longer required. Before we get into the architecture, I want to mention briefly about AWS IoT Core. It is the main mechanism which you're using to ingest the data from the device itself and then route it to destinations. On the top left-hand corner, you see an orange box there that represents the device gateway. This is the main entry point for the devices themselves. AWS IoT Core also has a message broker system built in, which allows us to have pub-sub types of models in communicating with devices and applications. The message broker is able to communicate with the device shadow, which allows us to store state for the device. In case the device goes offline, the device shadow can maintain the last known good state of the device, and we can get that data from an application using an API call. The message broker also can speak with and interact with the IoT rules engine. In this case, the IoT rules engine allows us to watch for a specific topic that the device is publishing data on, and then route that data to a destination. IoT rules engine supports multiple destinations such as Amazon DynamoDB, which is a NoSQL data store, AWS Lambda functions can also be invoked, which can carry our business logic and code without managing servers. And also we can target Amazon Kinesis data streaming platforms. Now let's take a closer look at the implementation we have in place for the TrueView platform for the IoT device connectivity. Starting from the left-hand side, we have the device communicating with the AWS IoT Core using MQTT, which stands for Message Queuing Telemetry Transport. It's a lightweight protocol designed for communication purposes for IoT devices. AWS IoT Core also supports MQTT over WebSocket and HTTP as well. Once we have the data coming in, we can watch, which is being published on a specific topic, we can have an IoT rule pick up that data and then route it to a destination. The IoT rule can be defined very simply. As you can see on the bottom left of the screen is a snippet of what an IoT rule looks like. It's a simple JSON schema. It uses a SQL statement to pick data from a topic and then has an actions section which routes it to a destination. In this case, for our implementation, we're taking advantage of the Kinesis data streaming platform. Kinesis data Firehose allows us to compress, batch, transform, and deliver that data to a destination. Amazon Kinesis data streams, on the other hand, allows us to look at the data as it's coming in real time, run analytics if you choose to do so, and connect to a custom application as a consumer. We'll talk about more of these endpoints that Kinesis Firehose and data streams are connecting to in the next section when we talk about data management. So once we have the data coming in from the IoT devices securely, and we're routing them to the data streaming platforms for Kinesis, now it was time to start running ETL analysis on that data, store it correctly into the correct data stores, and manage our own data lake strategy. The challenge we're addressing here is that once the data was available on the laptop in the field, surely we could run manual workflows and analyze the data, but we didn't have immediate insights into the data being ingested. Our solution here was to create a data lake strategy centered around Amazon S3. And we also wanted to leverage purpose-built data stores, specifically Amazon Redshift, which is a petabyte scale cloud data warehouse, and also Amazon RDS, the relational database service. Amazon RDS powers many popular engines such as Postgres, MySQL, etc. Once we have the data in these data stores, we could then run our ETL workloads on it, such as big data analysis. In this case, we chose to use Amazon EMR, formerly known as Elastic MapReduce. Amazon EMR allows us to run popular open source big data tools such as Apache Hadoop, Apache Spark, and many more. Overall, our solution was event-driven, so we didn't have to worry about manually addressing the data and the ETL portions of it, where it's going to be stored and how the work is going to be done. Let's take a look at what this process and architecture looks like. Let's picking off from where we left off in the previous slide, where the IoT rules for sending data to the Amazon Kinesis data streaming platforms. Let's start with the top section here. So we have data coming into IoT. It's being routed by IoT rules. We're sending it to data Firehose. Firehose, as I mentioned before, allows us to compress and transform data. In this case, for the transformation section, Kinesis data Firehose allows us to call an AWS Lambda function directly. AWS Lambda function carries our business logic and is able to perform simple standardizations on the data for us on our behalf in batches. Once that batch is complete, Amazon Kinesis Firehose receives the data back from the Lambda function, which it can then forward on to a destination. Kinesis Firehose supports connecting with Amazon S3 and Amazon Redshift, which we talked about a bit earlier. In this case, Amazon S3 is being to store the raw data as it's coming in from the IoT side. In case something goes wrong with our Lambda function or a code break, or perhaps we want to change and do different types of transformations, the raw data is then available for us and for our data scientists to work with. The data finally lands in Amazon Redshift, and from there on, we can start doing our big data analysis on it. In this case, as I mentioned before, Amazon EMR is being used. Amazon EMR in our case is running PySpark jobs. PySpark is a Python API for Apache Spark. The way we are triggering Amazon EMR is through a simple cron-based job running in an AWS Lambda function again. Our code can simply call the Amazon EMR cluster and job and then run our workload with it. And you can also pass in parameters specifically for our workload. AWS Lambda function is being triggered on a schedule using CloudWatch events, which is now known as Amazon Event Bridge. So we have the data being stored for our main ETL work. We also wanted to capture and store data from the IoT device logs, for example, from the device itself directly. In this case, we chose to use Amazon Kinesis data streams for real-time ingestion into the enterprise Splunk instance that's being used at Baxter. This allows us to ingest data directly as it's coming in. We could run analysis if we wanted directly on the Kinesis side, or we could do that directly in Splunk once the data is aggregated. So now we have talked about, so far, IoT data coming in, our data being stored, and our ETL process is running on the data itself. Once we had the data lake strategy established, we wanted to give access to the data to specific users. Let's take a look at what that looks like. In this case, the challenge we were addressing here is that distributing software to laptops in the field was a bit challenging, and also it was difficult to manage day-to-day access. For example, if you want to give more feature-rich access to different endpoints. The solution that we came up with was to create a reactive web and mobile application where we could create richer user experiences, update the user interface, add more features, and release these very rapidly in comparison to updating laptops in the field. We also added on Amazon API Gateway as the entry point for our data stores. Amazon API Gateway allows us to manage APIs at scale, and it allows us to add in custom authorization mechanisms ourselves. In this case, a unified API endpoint would be applicable for both the web client and the mobile client, regardless of where it's coming from, and we could manage our data sources underneath directly. Let's take a look at this implementation. On the left-hand side here, we see the web and mobile application clients. Both clients can first authenticate the user against the enterprise IDP, in this case Okta. Once authenticated, the users access the application. The application can then talk to the Amazon API Gateway endpoint, where our backend stores are located. Amazon API Gateway endpoint integrates with a custom authorizer. In this case, it's an AWS Lambda function, which can evaluate the incoming request, check it against a policy which is stored in Amazon S3, also check it against the Okta APIs, and then decide whether or not the user and the specific resource and method that they're using should be allowed to go through or not. If it's determined that the user and the request should be allowed to go through, the integration then passes it on to another Lambda function, which serves as a proxy to our backend data stores. Our backend data stores in this case are Amazon Redshift and Amazon RDS Postgres. The Lambda function is using SQL statements to talk to these data stores directly. Important thing to note here is that our policy on the custom authorizer side is stored in S3, so we're separating our policy directly from our code. Once we had the web administration portion established, we also wanted to be sure that we take a look back and integrate into any missing enterprise services that we needed to connect to. And we'll do a recap on the services we've connected to thus far and then move on forward toward the CI/CD section. The challenge that we were trying to address with integrating with Baxter Enterprise Services is that the existing field distributed laptops needed improvements on the logging, monitoring, and identity management portions. And it was also difficult to improve this situation quickly and integrate centrally. The web applications that we put in place enabled us to speak with Okta and added on a seamless single sign-on experience. Likewise, we could also talk to Okta from our API gateway layer directly and verify that the request should be authorized to go through, with both authentication and authorization put in place directly. We're also integrating with Splunk for IoT device data that's coming through, specifically for logging. One additional integration that we have made with Splunk here is also aggregating CloudWatch logs directly into Splunk. And we're using CloudWatch logs in two different ways. Let's take a look at this implementation. We've talked about the bottom portion here, the client devices talking to API gateway and then integrating with Okta. We've also talked about the IoT rules talking with Splunk through data streams. Another integration that we made with Splunk was through CloudWatch logs. In this case, the benefit that we gained here was that any native AWS services such as AWS Lambda would be emitting metrics and also application logs. We could evaluate those logs, gain insights from them, and take action as needed directly in the AWS services, instead of waiting for the data to be aggregated first in Splunk and then taking action afterward. However, this twofold approach allows us to do both, take action natively and also aggregate data for the long-term processing and analysis directly into the enterprise-wide Splunk. So we have data coming in, we have data being analyzed and stored and analyzed, we have data access being given to specific users, we have authorization mechanisms in place, and we have Baxter integrated services enabled. Then one important part that's coming up next is the CI/CD portion itself. Now that we have the infrastructure architecture pieces, how do we deploy this out? How do we create it? And what other integrations are there left to do? Let's take a look at that piece. The challenge that we're addressing here with CI/CD pipelines, which is continuous integration, continuous delivery in our case, is to figure out a better way of doing deployments and management of deployments compared to on-premises. The current challenge was that there could be monoliths in place with both infrastructure and applications, and it would be difficult to deploy out quickly. Likewise, it may be difficult to set up multiple regions and multiple environments at a rapid pace. And the current processes and systems which were in place usually took multiple days to both do the development and deployment with. The solution that we came up with here was to integrate into Atlassian Bitbucket as the enterprise service of choice at Baxter and marry that with the AWS CI/CD ecosystem. We also, along the way, added agile methodologies and took ownership of the product itself. So the previous infrastructure that I've talked about, from IoT to standing up the data analytics portion and data stores to the API gateway layers, all that is owned by this team. Overall, this allowed us to iterate and deploy infrastructure and applications separately. We started to analyze which tooling would be best, and we settled on 3 specific tools to use in order to create our infrastructure. First was AWS CDK. AWS CDK is a cloud development kit by AWS. It allows us to define our infrastructure as code in popular languages. In this case, Python was being used. We also added Boto 3 so we could do introspection on the deployed infrastructure, gain valuable insights, bring back data to help us make more intelligent decisions when deploying infrastructure. And we also added on AWS SAM, which is the serverless application model. AWS SAM allows us to define the API layers and the integrated Lambda functions. And for the API layers, we're using OpenAPI, which AWS SAM supports, creating APIs much more user-friendly. AWS CDK in our case was being used to lay down the major foundational infrastructure, such as standing up Redshift, RDS, Amazon S3, etc. Let's take a look at the CI/CD pipeline, which enables this workflow. In this diagram, we can see from the left-hand side that we have Atlassian Bitbucket integrated with Amazon S3. And from there on, we're triggering an AWS code pipeline. AWS code pipeline is an orchestration mechanism where we could build, test, and deploy our code and our infrastructure as we see fit. AWS code pipeline is pretty flexible. We can create multiple stages, have multiple actions, and either in parallel or in serial in those stages. And we can also invoke various integrated AWS services, such as invoking an AWS Lambda function or invoking an AWS code build job. AWS Code Build provides an environment for us where we can run our CLI commands mostly. And in this case, this fits perfectly well with the types of tooling we're using. For example, with AWS CDK, we can run CDK deploy commands directly in Code Build. With AWS SAM, we can run package and deploy commands from there as well. AWS Code Build runs an instance where our jobs are executed and that instance is shut down. So it's up for the duration of the actual workload being run. In this case, AWS Code Build is being leveraged for building, for testing, and for deployment purposes. And the one integration that we added on here besides Bitbucket was to be able to communicate with the operations team any issues that may have come up during the build, test, or deploy phases. So for example, if a test failure would have occurred, we would have been notified on our Slack channels. Overall, in creating this architecture, the foundational work was done with AWS ProServe, but then the platform team at Baxter did a phenomenal job in both carrying it forward, adding in CDK, adding in multiple pipelines, being able to deploy this infrastructure and applications at a moment's notice. Throughout this architecture, we also leveraged the AWS well-architected IoT lens for foundational best practices. The architecture we built was native to the cloud. It was modular. The infrastructure cost in comparison to on-premises was near $0 for OpEx and commercial off the shelf. And we also gained greater than 50% annual run rate savings. Along the way, we added almost 78% in integration testing alone, and that number continues to climb. We also gained the benefit of having automatic scaling for infrastructure and connected devices, and due to the addition of Amazon Redshift, we now have a petabyte scale data warehouse at our disposal. In comparison to on-prem, where it could have taken several days to deploy infrastructure, now with this setup in place, we could deploy globally within hours instead of days, including any handoffs or security reviews that may have to take place. The Baxter team has thus far added 250 plus AWS certifications and counting, which is a really great achievement. To recap, we were able to address the secure communication from the device to the cloud. We also addressed how to do data management and data analytics by standing up our infrastructure there with both Kinesis Firehose, routing data to Redshift, our ETL workloads running in Amazon EMR. Once the data was in place, we also described how administration of that data can take place using reactive web applications built on top of an API gateway layer. We also, along the way, integrated with several enterprise services such as Okta as the IDP, Splunk for logging and monitoring, and data aggregation, as well as Bitbucket as a CI tool of choice, and Splunk for communication purposes. Lastly, we also added agile development methodologies and use CI/CD to both deploy, test, build, and deploy our infrastructure and application code. Now I'm going to hand it over back to Mike for his key takeaways.
Thanks, Sharar. Great overview of the solution. And, it's been amazing. All of this came together while we've been working remote, during COVID, during a time that probably work has never been more challenging. And it's impressive to see it presented this way. So we wanted to wrap up the presentation, share a couple key takeaways and learnings. Again, really an advancement in how we're doing cloud native architectures. It's now becoming part of our DNA. Scalability, cost, reliability, security, and automation. The cybersecurity in these devices is, on any medical device, is critical, and we've identified ways to kind of separate the design from change. My finance teams in particular like the cost piece of this. There's zero fixed cost or upfront off-the-shelf licenses that we need to buy. As we've moved around the globe, there's a desire to keep data resident. And so the work we've put into the pipelines make us very portable to be able to move this solution between AWS regions due to the serverless design. So my three key takeaways, and I'm even a little bit remiss on how we presented it, Sherry, are we probably should have started with the pipelines. Reflecting on it, you want to spend 60 to 70% of your time up front on the development environments and the pipelines. Oftentimes within technology, the cobbler's children have no shoes, but the work we've done up front on the pipelines for consistency of deployment, the configuration management of our environments has been critical. Again, 60 to 70% of your time in development, 20% in test, 10% on prod. Really, our old world used to be upside down. Use of AWS services for speed. Using the native components that we have available to us so that we focus on the therapy instead of the technology. AWS has been a great partner for us, and Sherry and the ProServe team in particular in helping us getting started, and then also giving us the skills to operate on our own. Finally, designing for change at the appropriate layer. The medical device can't move as quickly as we can within the cloud, so creating a design and a plan to take advantage of the best of cloud while protecting the medical device. So again, Sherry, thank you for the invite. Thanks to the entire AWS team for helping make this possible.